Hello, my friends. In this video, we are going to talk about Lorentz force. Suppose you have two magnets and the magnet itself have a south pole and north pole. The magnetic field is going out of the north pole of a magnet, and then you will end up with you will pass to the south pole of the other magnets. And let's define the direction in three-dimensional space. And the direction here is x, and the direction here is y. So the horizontal axis is the y-axis. And finally, there is a direction in the vertical direction. In this case, the magnetic field is running horizontally in the y direction. Suppose we have a long wire. The wire is running in the x-axis. And the wire is carrying a current I. The length of the wire is L. According to Lorentz force, you will have a force. And the force is given by I L cross B. And according to this formula, the cross product between L and the magnetic field B will end you up with a force. In this scenario, the force is heading upwards. So there will be a force going upwards. L. And this is the meaning of Lorentz force. Now, suppose we have another experimental setup against with two magnets. And sorry, there's an N here. And we also have magnetic field running from the left magnet to the right magnet horizontally in the y directions. Now this time, let's assume we don't have a wire, but instead we have a charge particles moving across the magnetic field. And the direction of movement is in the x direction. So this is the charge, and it's moving in the velocity v. It's moving at the velocity v. What is going to happen? Now, we have this formula. We know that the force is given by I L cross B. But I is given by dq dt. And if we substitute I into equation 1, then what we are going to get is the force, and then del Q, the derivative, time derivative of Q, and the funny thing about calculus is you can move the del variable around, and in this case, we can do that. So eventually, we will end up with a equation, a new equation, Q times the time derivative of the length, and then cross product with the magnetic field. But hang on a minute. What is the time derivative of the length? Shouldn't it be the velocity? So this is the new formula for the Lorentz force of a particle moving across the magnetic field. So in other words, in this case, if the charged particle is moving in the x direction, while the magnetic field is running in a y direction, and according to the formula given here, we are going to have a force given by Q times V cross B, where V is the velocity, B is the magnetic field. And in this case, there should be a upward movement. There will be a force pulling upwards. So the charge is not going to be moving in x direction only. Instead, it will gradually going up. So this is the nature of the Lorentz force for a charged particle moving across the magnetic field. And suppose, in addition to the magnetic field, you also have an electric field around. And suppose you have a positive electrons up and down. Theoretically, due to the presence of the voltage across these electrodes, you are going to have a electric field running vertically from up to down. So the charged particle will experience a magnetic field and also a electric field E here. And the force will be influenced by the combined effect of the magnetic field and the electric field. So finally, Lorentz conclude that the total force is given by the electrostatic electrostatic force, which is Q times the electric field, and the electric field here, E, is given in a vector. And then we have the Lorentz force in the second term of the equations. And the formula can be simplified into so this is the final conclusion of Lorentz theory. Lorentz theory. Thank you.